Okay, let's get started. So last time we discussed the electronic defects. Or in other words, we studied electrons and holes in semiconductors. So basically electrons and holes in semiconductors. So we gave two different kinds of explanation on, or different kinds of treatment on how to approach this question. So the first one is we follow the concept of defect reaction. So essentially we write a defect reaction, a defect chemical reaction, something like this. So basically that's the formation of electron hole pairs. Okay. Now we know that the electron is in the conduction band and the hole is in the valence band. Okay, so then we just treat the electron and holes as in just a normal point defect in ionic crystals. We know that we can write n times p. Basically, n is number of electrons and p is number of holes. It's basically nc times nv. Maybe let me write something like this. The exponential minus kBt and Eg here. Okay. So these are called effective density states in the conduction band or valence band. So essentially, if we say, okay, if we have the intrinsic region, basically if we have the number of electrons is equal to number of holes, then this can be easily calculated. Basically you take a square root, something like this. Okay. So of course there is assumption going into this thing, because there is assumption that we can write something like this. Of course, we want to write Eg is not much larger than kBt. Okay, so this is basically the assumption. So therefore, if you look into, let's say, conductivity, so if you plot logarithm sigma, sigma means conductivity, or something like silicon, or 1 over T. So usually what you find is that in this kind of called intrinsic region, so it's intrinsic, which means no dopants. So you basically have some activated. So again, the slope should be 2 kb and Eg here. Okay. So, which means that because the conductivity will be proportional, if we assume that the mobility does not change, the conductivity should be proportional to the number of electrons and holes, something like this. So as you can see that if we go to pretty low temperature, if you go to so-called intrinsic region, the higher temperature is, the higher conductivity of the semiconductor is, simply because you have more electrons than holes. Okay, so if you're going to higher and higher temperature. Okay, so this is basically treating electron and holes as defect as point defect. Okay, so it's basically the defect chemical reaction. Of course, this is kind of, you can argue that we neglect a lot of details and they are, electron and holes, they are in fact not point defects. So then we also introduce the kind of band theory. Band theory. So essentially, we really go into detail to look into the physics of semiconductors And we know that the reason that semiconductors are called semiconductors is because we have valence band here. We have conduction band here. Okay. Then, of course, we have electron-hole pair because some electrons are thermally excited from the valence band to the conduction band. So we have holes here and electron here. Okay. And of course, this is called band gap, e.g. here. And last week, we spent a lot of time to talk about energy dispersion and density states, so on and so forth. So at the end of the day, what we get is basically, if we say this is the Fermi level of the electrons, then we can basically calculate the number of electrons in the conduction band, the exponential minus EC minus EF over KBT. So this is basically telling you that the distance between the conduction band and the Fermi level, because this is EC, this is EV. So this distance is giving you the number of electrons. Okay. So if we move move the Fermi level towards the conduction band, then of course we have higher and higher number of electrons. Okay. So we can also write the number of holes as NV exponential minus KBT over EF minus EV. Okay. So basically, then the distance standard here is this guy here. Okay. All right. So we also show that in reality, I mean, these two languages, the result you get from just treating the electron holes as defect chemistry, as defects and using defect cryptographing, or if you really go into detail in physics, if you treat the electron holes in band theory, they are pretty much the same. At least in what we want to study. Okay, of course, if you go to study more advanced topics, or if you go to more quantum physics, then there are important differences. However, for this course, it's pretty much sufficient. Essentially, you can either go into this, which is much easier, or you know that behind it you have more physics. You have band dispersion, you have density states, you have something like this. Okay. So, however, last week what we talked about are intrinsic. Okay, so it's essentially here we have intrinsic, which is no dopants. But we know that for semiconductors, it's very important that we have dopants or extrinsic or doping. Okay, so for example, if we take the prototypical silicon as an example, if we have silicon as a semiconductor, then we know that we can either dope with donor dopants. We can have donor dopants. The most commonly used is basically phosphorus. Okay, so if we dope phosphorus into silicon, we know that there's a difference between number of electrons between these two, right? So this one is just one in the periodic table, just 1 over. So what it does is basically has the positive charge and then balance with the negative charge. Okay. Or in more general, you can write it as the dopant in E and with electrons. Okay. So I mean, if we say every single phosphorus doped into silicon is become positive and donate 1 electrons, what we can simply write is basically, let's see, the number of electrons is essentially the same as the number of dopants. Okay. right? Then from here, what we have is the, let's relax a little bit and let's just write E and H is basically exponential over kBt over ET. So, and if you take this and if you take that, you can actually calculate the H is basically, let's call it KEL. Now, of course, KEL is function of temperature. It's basically KEL over electrons, or it's basically dopant concentration. Okay. Since when we dope the system, usually we use at least higher than extrinsic. Okay. So this, so as you can see here, if intrinsic, what you have is basically this one equal to this one equal to square root of KEL. And this thing will be much larger than KEL. Okay. So if you follow this, and what you end up with is basically now we have, more electrons than holes because it's p-type, it's n-type, or it's called n-type. Okay. So this is basically the treatment using the language of defect chemical reaction, right? So basically you have the defect chemical equilibrium, and just do this, you get something like that. Of course, you can also use the band theory to do the same thing. Okay, let's see if I, let me erase this one. So, in terms of band theory, what it does, if we put a dopant in, is that we are going to introduce the dopant level. We are going to introduce a dopant level called ED. Okay. So basically, that's still within the band gap. And what it does is basically move the Fermi level to here. Okay. So what it does is basically, if I have donor dopant, then what we do is basically we have EF is ED. Okay, so basically moving to very close to the conduction band. Okay, let's see what it does to the electron and hole number. For the electrons, now we have NC exponential minus EC minus ED kBt. Okay. You can see here, this guy now is much larger than exponential 2 kBt Eg. Right? Simply because this is much closer. It's a much smaller value. There's a negative sign here. Okay. So also you can imagine that questions? No? Okay. You can imagine that we can also have a sector dopant. A sector dopant. For example, we put boron into silicon. And boron is of course pretty much 3+, so you can dope with hope. Okay, so essentially what we can also write is basically A as an acceptor, then we dope the system with hope. Then it's p-type. Again, if we follow what we talked about using this kind of defect chemical reaction language, we have the number of holes will be fixed by the number of the acceptors. Of course, we know that this is not the electron neutrality condition, right? The real electron neutrality condition also have this one, also have electrons, right? But because in the case we have the number of holes much larger than the number of electrons, right? So we can say this is roughly the same. So it's roughly the same, and we can just neglect this one for a second. Okay. Of course, we have the number of electrons. Now it's again predicted by the defect chemical equilibrium, KEL over H, or it's KEL over the number of sectors. So again, this is much smaller than the holes. So that's why we have this assumption in the beginning. Okay. So equivalently, we can also go to the Venn diagram, or it's kind of in the Venn diagram to say the same thing. Okay. So now what we have is we have the acceptor level in the valence band. So let's call it EA. Then EF just moving downwards. Okay. Then if we have, I'll just write here. So acceptor open. Then EF should be something like EA, which is very close to the valence band in this case. Then we have, again, now we first have P, which is central minus EF, or now EF is just EA, right? Minus EV over KBT. Again, now this thing is much larger than exponential minus 2EG. KBT. Okay. Of course, if we think about the so-called, again, so this thing and this thing here, now they are called a majority charge carrier. Because there are many of them if you dope the system, right? So this thing is now called a minority charge carrier. Okay. Because we are few of them if we dope the system with either donor dopant or acceptor dopant. Okay. So we can also see that if we follow the Venn diagram, for example, if we have donor dopants, the formula is up here, then of course the holes become minority charge carrier simply because this distance is very large, right? So if you plug this thing in, so you have the negative sign here, so so this is much larger than the holes. Again, this is much larger than electrons here. Okay. No problem, right? Okay. So, okay, this is how we treat the dopants. Okay. So I think since we are since it's really a physical chemistry class rather than semiconductor physics class, so I just give you another way to look at the problem. So another way to look at it is think about the chemical potential. So what I mean is that the third way is to think about the chemical potential of electrons and holes. Electrons and holes. Okay. So again, everything here we are basically reduced to Boltzmann statistics, as you can see here. So basically, we forgive that the Fermi-Dirac will be reduced to Boltzmann. Anyway, so if we have that, so what we can write is basically, if we simply think the chemical potential of electrons is basically the chemical potential of electrons at the standard condition, we'll know in a minute what these things really are. Okay, plus RT. Okay, but for the sake of the unification of the unit, I'll just write it KBT. For maybe the last time, I'll just say these are quite equivalent because KBT plus times Avogadro constant is basically R, right? It's basically so depends on how you look at it. And logarithm the fraction of electrons or number of electrons. Okay, so it's just simple like that. Okay, and then we can just simply solve for this guy, for the fraction of the number of electrons, and we can write it basically exponential negative. Just put it over there, KBT. Because I put a negative sign here, right? So let's see. Okay, then we put a. So basically, I move this guy here. Okay, so first we have this guy. So if I move this here, there's a negative sign here, right? So first this guy, then this guy. Okay, no problem, right? So if I compare this equation, with the equation we have here. So let me remind you, this is nothing but n over nc. Okay. So you will see two immediate consequences. Okay. So you see there's negative sign here, the negative sign here, then the KBT is the same. So what you end up with is you will immediately know what these two values are. So basically, you will immediately know. So this is basically the Fermi level. So which means that the chemical potential of electrons is the Fermi level. So in solid state physics, it's often directly written in the textbook, which means the concept of Fermi level is basically the same as the chemical potential. Potential of electrons. Okay, so in a lot of the solid state physics textbook, you will find this conclusion. Of course, it's not 100% correct. So what I want to say is that later we're going back to this. So it's actually electrochemical potential of electrons, because sometimes you can have electric field and electrostatic potential. But let's not go in there just yet. So for here, it's sufficient to know that the chemical potential of electrons is basically Fermi level. Okay. So there's another equivalent, which is the standard term here. Okay. As you can see, the standard term is just basically the EC. So EC is basically the conduction band minimum. Okay. So this is basically saying that the conduction band minimum is nothing but this guy here. So you can also see that if I using this EF as EC, right? So this exponential part will be just 1, right? Which means that the number of this will just be 1, or the number of electrons will be the same as this one. So which means every single density state will be occupied. So this is basically definition of the standard condition, which means that you have the kind of unity of the concentration or unity of the electron. Okay. So, I mean, this is electrons. We also need to do holes. I mean, so this is no-brainer to just write this guy, and let's write KBT. Okay, so I mean, you can just write something like this, right? So you can also write. So this is basically the same KBT and UH. Okay. However, what we want to write is a little bit more complicated. Okay, so let me see. So so I want to write a little bit more complicated. So it's basically I will write it in another way. I'll explain why that is in a minute. Again, okay, so basically I did nothing here, but just move this to the front and put a non-negative sign here. I did that for a reason. Okay, so if I again compare this equation with this equation here. Okay, and what we can see immediately again. There's basically two convolutions. Okay. So EF will be negative mu h. Okay. So this looks a little bit strange, right? So why now EF is negative chemical potential of holes? Okay. So this can be. Let me just erase this part. So this can be actually quite easily rationalized by thinking about the chemical reaction, feedback chemical reaction. Sorry. It's the electron and holes. We know that. So for this feedback chemical reaction, if we reach equilibrium, the equilibrium condition is basically the mu E plus mu H will be 0, right? So this is chemical. So for this chemical reaction, so this is the condition for reach equilibrium, right? So I mean, if you follow this, you can easily write this chemical potential will be negative of this one. Okay, and we know that this guy is EF, is Fermi level. So, I mean, apparently, so Fermi level should be negative of the holes. Okay, so this is not usually mentioned in solid-state physics because people usually just think about the Fermi level as the chemical potential of electrons. But if we follow this defect chemical reaction, we'll know more. Okay, so you can also easily see in the band theory that so if you move up the electrons, if you move up the Fermi level, you have more and more number of electrons, but you have fewer number of holes, right? So which means that the concentration will be lower and lower. So there has to be the negative sign. Okay. Again, so if you compare this one with this one, so another thing you can get is the EV. It's basically negative the standard condition, standard chemical potential of holes, right? So which we can rewrite is basically we can rewrite the band diagram, which is very typical, prototypical in semiconductor physics. to be totally in the chemical language. Okay, so what we can rewrite is basically this is the convention band, this valence band. Okay, so then we have this is EC, this is EV. So that's in semiconductor physics language. But we know, so this now should be the standard chemical potential for electron. So this will be negative standard chemical potential for holes. Okay. And again, we know that if we have Fermi level, it will be the same thing as the chemical potential of electrons. Okay. Or should be negative chemical potential for holes. Okay. So this is basically the way to rationalize semiconductor physics from the point of view of defect chemistry or from the chemical potential. Okay. So essentially we have three ways to look at this. So we have basically three ways to look at this, either from the defect chemical reaction. Okay. So basically the defect chemical reaction basically is this. Okay. So if you reach the chemical equilibrium, you can predict the equilibrium number of holes and electrons. Or you can get it from the band theory or band diagram. So the third thing is that you can get it from the chemical reaction. So if we think of the basically the EG is much larger than KBT, or it's not strictly kind of quantum mechanics. We basically reduce the Fermi draft distribution to Boltzmann statistics. Anyway, just write Boltzmann. Then these three languages are basically quite equivalent. You can just choose whatever you like the most. Okay. Of course, they tell you different things, and different people have different preference. Okay. So for me, I personally like the third one because it kind of tell me it kind of makes sense to me. For example, I'll give you an example. It's actually a very simple example, but we're going to come back to this later in the semester. Basically, the example is Qiyang junction. Okay. So Qiyang junction is basically you put a piece of p-type semiconductor with a piece of n-type. Okay, for example, you can have silicon doped with, let's say, boron here, and silicon doped with phosphorus here. Okay. So if you read the textbook of semiconductor physics, what you usually get is treatment like this. Okay. So again, so since they are both silicon, their conduction band and valence band should be the same. Okay. I mean, the same here. Okay. However, they are doped differently, right? So for p-type, we know we have more holes than electrons, right? So the Fermi level is pretty close to the valence band. Right? For n-type, it's up here because we have more electrons than holes. Okay. I mean, what if they get into contact? So, I mean, if semiconductor physics, what people will tell you is that so rule number one is that you have to have fixed formula at equilibrium. Okay, we'll talk about what that means later. Okay, now so basically this is junction equation. So let's imagine this junction. Okay, so far away from the junction, let's say if you go to far away from the junction, you still have valence band and conduction band here. So it's valence band, conduction band here, and valence band, conduction band here. However, near the junction, since the formula was fixed, now the only choice we have is that the conduction band and valence band is going to change. So this is a very typical band diagram for p-n junction. Okay. So basically, far away from junction, everything should be exactly the same as before. Inside the junction, you are going to have something different. Okay. So one question is, let's just think about this point, which is inside the junction. So you can see that in this case, the number of holes and number of electrons, they are both pretty low, right? Because they are this point, the conduction, the valence band is here, conduction band is here. So which means that if you think of this exponential term, so this guy is pretty large. This guy is pretty large. It's almost like formula with middle band gap. Right, so which means that the charge carrier density is very low for both electrons and holes. So therefore, it's called the depletion region. However, this for me can be a little bit hard to understand, right? So I see some of you are having difficulty following me. Okay, let me tell you another very simple story, which is maybe easier to understand. Okay, so let's, for example, think of a little in a minute so let's think of the chemical potential of electrons, basically mu e. Okay, we know that for the n-type, mu e should be pretty high. Okay. So for the p-type, mu e should be pretty low, right? So because mu e is mu kBt log e, right? So if I say, okay, mu e is here, mu e is here, if I put these two things into contact, so there'll be more, there'll be electron diffusing from here to here, right? So there'll be a driving force here. So end of day, you're actually connecting this thing this way. Okay, so I mean, there's a reason why there's this part in the middle, because there's electrostatic driving force, which we are going to discuss maybe 1 week later. However, the rationale is basically you have the kind of the chemical potential kind of continuously going down. Okay. You can also draw the mu h, and the mu h is here. And again, you have the continuous going down like this. Okay, now you can see that in the middle, the mu h and mu e, they are both pretty low. It's lower than this one and lower than this one. So that's why the condensation is pretty low. So these two pictures, they are pretty equivalent. Basically, you can choose whatever you like. Of course, if you look into semiconductor physics, they usually use this language, but equivalently, you can use this language also. Okay. So, okay. So it's okay that if you are a little bit confused about this, because we are going to come back to this later in the lectures, so you understand more. Okay. So I think I'm going to give you the last example, which is the so-called band diagram. Of course, with coordinate mass of ionic defects. Okay, so what do I mean? Okay, let's think of the anti-Frankel defect. In, let's say, sodium chloride. Okay, so basically you have the formation of a pair of chlorine interstitials and chlorine vacancy. We have been studying this for quite some time, right? So of course, the concentration can be something like this. Should be potential minus RT delta mu reaction. Okay. So what we want to know is actually so what we can write is that if we do not think of this as the defect chemical action, let's say if we write the individual chemical potential, so this thing should be let me think about it. Okay, let's do this. Let's see. So this one should be mu RT logarithm. Okay. So then you can basically rewrite negative RT. Okay, so now what we can imagine, or we can assume that you can actually have anti-levels. Okay. So let's say, so this anti-level is mu this guy. Okay. You can also define sorry, it's not a standard condition anymore. So this is basically one-to-one mimicking the band diagram, this one. Okay, and of course the distance here will decide the concentration or the fraction of the chlorine interstitials, right? So you can also write this guy. Okay, then of course should be exponential minus. Okay, let me write it. Let's see. So negative. Okay, so basically what I want to argue is this is equivalent to electron. It's equivalent to holes. Okay. So you can say, okay, so this is basically negative. And we know that if we reach the chemical equilibrium for this guy, so the chemical equilibrium gives you the summation of these two should be 0, which means that this so-called formula over here should be negative of or that vacancy. Okay. Right, so we can see kind of basically equivalent. So this is kind of equivalent to the EC. So this is equivalent to EV. This is equivalent to EF. Okay. So basically, this will give you another perspective to look at the ionic effects from the kind of the bands or the anti-levels. Of course, there's a very important difference between electron and holes and defects. And this is defect. This is basically this guy. Okay. For the ionic defects, essentially the picture is like you have a bunch of ions, right? Okay, you have a bunch of ions. So basically you remove the ions, okay? Let's say if you create a vacancy. You basically take the, you have the, let's say, n state, and you remove one of it, okay? So, so basically, you will remove this one, or remove that one. So they are essentially has the same energy. So which means that then is basically the same so same energy. So which means that if you draw, so this energy, so this is Ne, or equivalent density state. So this be a delta function. Okay. So which means that all the density states essentially have the same energy. However, here we know that if we know that the density state looks like this. So basically, this is proportional to 1/2 of the energy. Okay. So that's the difference because ions are really ions, but electrons, you have to use quantum mechanics for the electron in the holes. But for equivalently, if you just think of the conceptually, you can essentially use the same language for ionic defects and electronic defects, at least in the study of solid-state ionics. Okay. Okay, so let's continue. So next we are going to discuss something very important in solid-state ionics. So which is called the Brouwer diagram. Or Brouwer diagram, and depending on let me just write it more clearly because it's Brouwer diagram. Okay, so what Brouwer diagram tells us or try to solve is this kind of problem. Okay, so we talk about the dopants in semiconductors, right? So, for example, we have silicon. We can either dope with the donors, and we have electrons, or we can dope with acceptors and the holes. Okay. However, I mean, these dopants you have to put into the system. They are kind of extrinsic, right? So we have to take a piece of silicon, you throw this dopant into the sample, right? Either using kind of, I mean, most likely using ion implantation. Okay. However, in a lot of things we study, so we can have it's kind of like a self-doping. Okay, what does that mean? So let's take an example. Let's say we have a piece of oxide. Okay, so the M is just for metal. For example, you can think of this copper or zinc. Okay, something like that. So let's say first it's a piece of ceramic sample. Okay, so of course for the ceramic sample we put it into in contact with certain oxygen partial pressure, CO2. Okay. So now let's say if I lower the partial pressure in the surrounding environment, we heat it up, okay. So if the temperature is sufficiently high, so what can happen is that it will reach the new equilibrium. So we're going to take some oxygen from the sample to remove some oxygen so that we can be in equilibrium with the PO2. Okay, so effectively, so what we can create is we can create oxygen vacancy. Okay. So basically, before we have the lattice oxygen, then we take that out to gas phase. However, we have to so basically we create oxygen vacancy. However, the sample has to be charge neutral. Okay. So the bulk of the sample or bulk of any crystal or ceramics or whatever you have has to be charge neutral. So you have to balance the charge. So the way to balance charge is basically you have two electrons. Okay. So now this is the similar to this case. Okay. To this case. To the donor dopant. Right. Essentially, what it does is you change the surrounding environment to create oxygen vacancies, and you create electrons. You put an electron into the system. Okay, now let's say PO2 is very high. So we increase the PO2 or we pressurize the PO2. Then oxygen will go into the sample, right? So let's say now it creates oxygen in the tissues. Now it's 1 plus delta. So then the oxygen basically goes into the sample, become oxygen in the tissues because oxygen is negative charge. Then you have to balance the system with holes, with holes, right? Now it's very equivalent to this guy here, this p-type. Okay, so basically so you can dope the system with the iron, which is already a constituent, basically, which is already part of the material itself, right? It's metal oxide, so you can manipulate the concentration of oxygen so that you can have different electron or hole dopant, or hole doped into the system. So this is basically the idea. It's kind of like self-doping, if you think of it, right? So what you change, of course, is this guy. Okay. So what you change is basically the log. We'll explain why that's a log. Actually, let's get that for a bit. Okay, let's say what you change is basically a PO2. Okay, then you this will change all the defect you have. You will change the amount of oxygen vacancies, the amount of the electrons, the amount of oxygen into tissues, the amount of the holes, right? So the Brownian diagram is basically the quantitative relationship between, let's say not between, basically between the chemical potential of something and the defect concentration. Okay, but the chemical potential of something, what does that mean? So if you change this one, we know that for the oxygen gas phase, you can actually calculate the chemical potential of oxygen gas, right? The chemical potential of oxygen gas phase is some kind of standard condition plus RT logarithm PO2. Okay. Right. So this is gas phase. So basically, when it's oxides, right, you can also define. What you do is you can also define the oxygen chemical potential for this guy. Okay, so if this thing increases, you'll see that you can have more oxygen intertissues. If this thing decreases, you will have more oxygen vacancies. So at the equilibrium, what you have is basically this thing for MO should be 1/2 of basically this is gas phase. Okay. So so this is basically another way of saying that you can always insert So you can always insert one more step. For example, here you can see that the oxygen first go into here, then here. Okay, something like this. Okay, so this is basically the chemical equivalent condition. Okay. So then in oxides, that's basically for mu O with defect concentration. Okay. So Brouwer diagram is basically tells you how to solve for this one, or equivalently how do you solve for, because this is basically RT log PO2. Okay. So in reality, people want to use the 10, the logarithm with 10 as the base. Okay, it should be mu, let's see, 2.303 RT logarithm. So that's now 10 as the base. Okay. So, or equivalently, it can be log Q2 with the defect concentration. Okay. So, I guess in today's class, we're going to show the kind of basic technique, how to establish the Brouwer diagram. Okay. So I think for next week, we're going to talk about more details. Okay. So basically, our question or our problem is that we have a material which is the some kind of monoxide, or can be copper or can be zinc oxide. And our assumption is that the majority or the main RD defect in the sample is basically oxygen vacancies or oxygen interstitials. Okay, so it can also be other things. For example, the cation vacancies, but here we assume that these are the majority. Okay, so these are basically Frankel or anti-Frankel pairs. Okay, so we also have electrons and holes. Okay, so basically we need to solve for this four. Okay, so our goal is basically to establish the quantitative relationship between log CO2 and this defect, and defect equals this 4. Okay. All right. So let's see how to solve it. Okay. So basically we have 4 unknowns, right? So we have 1, 2, 3, 4. 4 unknowns under one fixed condition. Okay. So that means that we have to have 4 equations, right? So we have to have 4 equations to solve for 4 unknowns. Okay, let's see how we can establish the 4 equations. So the way to establish these 4 equations is by recognizing the defect chemical reactions. The first one is basically we have the Frankel pairs, right? We have pairs of oxygen interstitial and oxygen vacancies. So basically some. So the first thing is we have Frankel pair. So basically none to oxygen interstitials and oxygen vacancies. So if we reach equilibrium, we can write that the should be exponential RT mu Frankel. However, here in Brouwer diagram, basically we don't change the temperature. We fix the temperature. Okay. if that's the case, we just say it's basically some kind of chemical equilibrium constant, Kn. Okay, so this is the first equation we have. So we also have so-called band-to-band excitation. So that's basically saying that we have electron in the holes, right? So we're going to write the same thing as we have been writing for the last two lectures. Basically, form a pair of electrons in the holes. Let's write a KEL as the equilibrium constant. Okay. So these are two kind of intrinsic defect time interaction, right? But we know that now we are dealing with some kind of self-doping or extrinsic. So we have to have gas exchange. Gas exchange. There's no covalent marks. So gas exchange is basically something like this. Okay. So let me just write the so equivalently we can write as the also in the tissue depending on which way you are going, but they are actually the same because end of the day you have the Frankel pair to connect these two. Okay, so let's say the equilibrium constant is Ko. Right, Ko should be again, if we follow the so-called mass action law, then the PO2 1/2 OO. So if we think that the delta, where do I have the delta, is actually much smaller than 1, which means we don't have a lot of the oxygen vacancies, then this guy is roughly 1. Okay, so we can develop all this guy here. Just something like this. Okay, so we have 1, 2, 3 from the chemical reactions. So we need to have the last one. The last one is actually charge neutrality. So the whole system has to be charge neutral, which means all the positive defects but pay attention to here because the oxygen vacancy has 2 positive charge, right? So when you have 1 of this thing, you have to put a 2 here. Okay, should be balanced by a negative charge. Okay. All right. So we have 1, 2, 3, 4, 4 equations, right? We have 1, 2, 3, 4, 4 unknowns. Okay, in principle, we should be okay, right? So, I mean, the parameters we have to know to solve this is basically the equivalent constant Kf, Kel, and Ko. So once we have know all 3, because this one there's no parameters, it's just charge neutrality. Once we know all 3, now we should be able to solve for 4 unknowns. Then we are fine, we are good. We can draw the boundary diagram. However, it's pretty. It's not that difficult because not everyone has their computer. You can just use some brute force. You can do trial and error, right? You can say, okay, first I have a trial solution for this guy, and you can, if it doesn't match, you can adjust that. You can try that. However, when boundary diagram was developed, there was no computer at all. Okay, that was before the age of silicon. So, of course, when you don't have the computer, you have to make an assumption to make it easier. Okay. So the assumption is that you can. So basically, the boundary diagram is the kind of, there's a trick to solve for that. The trick is basically look at this. Okay, so the charge neutrality looks too complicated. So we can apply something as so-called boundary condition. So boundary condition is for simplifying electron neutrality. Electron neutral condition, neutrality condition. So essentially, the way to do that is pick two majority defects. These two have to be one negative and one positive. Why? So when you pick two, we'll say the two majority defects are both positive, you can never satisfy the charge neutrality, right? So essentially, you have four unknowns here. So the way to simplify it is like we just pick two of them. Can be also vacancy and electrons, and you say, okay, we neglect these two. Then we put it to here. Then we can solve it. Okay. Well, easier said than done. Okay. Let's see how we actually do it. Okay. So let's say we divided the PO2 log PO2 range to three regimes, 1, 2, 3. Okay. Anyway. We'll know what that means later. Okay, let's say regime 1, which means so-called Austin pool. Austin pool, which means that you have many of Austin vacancies, right? So which means that you have many Austin vacancies, much larger than the number of Austin intertissues. Okay. So imagine that if you have a system, let's say the MO, you lower the PO2 by a lot, then the Austin gas will be evolved, and you leave many Austin vacancies inside the sample. And you don't have many of Austin intertissues. Okay. So let's go back to here. So the first thing is that you don't have this anymore. Okay. You only have this one, right? Then of course now pretty much you have many electrons, right? You have many electrons, then because electron and whole number, they are fixed by this thing. Okay, so then you can also neglect this one. Right, so this is the way to simplify the question, because you can just take two out, then you just have one equation here. Okay, then the simplified charge neutrality will be the number of Austin 2 is basically the number of electrons. Okay. Alright, so once we have this problem is solved, because we can just plug this into this equation here. Okay. So basically I say KO is Q2 1/2 Austin vacancy, then electron squared. Okay. Then the electrons is basically 2 times of Austin vacancy, right? Then this is PO2 Austin vacancy cube 4, right? Then we basically have Austin vacancy somewhere like KO 1/3. Then the anyway. One-third, then Q2 1/6. Okay. Then of course the electron is basically 2 times that one. Okay. Okay. So what about the holes and oxygen institutions? Of course they are of very low concentration, but they are there. They exist. Okay. Then the oxygen institutions should be Kf over oxygen vacancies. Then you should just plug this in Kf, KO 4 1/3, then CO2 1/6. Right. Then from this guy we have holes. It's basically KEL over electrons. Then it should be 2 or 1/3 CO2. Okay. So I mean, in Boundary diagram, because it's very difficult to write all these equations, and we're going to do it 2 more times. So the way to do that is basically plot like this. Okay. Let's say this guy is log PO2. So this guy is log P fact. Okay. So I mean, if you take just let's say let's take this one. Okay. So if you just take a log of this, and then if you plot with log Q2, right? So the power is basically negative 1/6. Essentially, you have something like this. So this oxygen vacancy, and if you see the slope, it's negative 1/6, R6. Right? Of course, electrons is very close to that. It's basically 2 times. So this is electrons. Okay. Of course, if you think of these two, they are pretty low in concentration, but they are there. Okay. So they are at pretty low concentration. And also, if you think about it, you'll see that this is Kf here and the KEL here. So when plot it, you have to be careful. Okay. So our assumption is Kf much larger than KEL. We'll know what that means later. Okay. So Kf larger than KEL, which means the band gap is large or small. Anyone? The band gap should be large, right? Because KEL is kind of small, right? Anyway, so when we think about that, then the institution is Kf over this one, right? So then the oxygen institution is like something like this. Then the electron and holes is like this. Okay. Again, they are 106. Okay. So this is first regime. Okay. You got it, right? I'll erase it. Okay. So we have another regime, number 2, which is called intrinsic. So intrinsic means that the PO2 is not too high or not too low, which means that this reaction is not really going that far. Okay. So which means that we probably have equal number of this in this. Okay, then if we go to the Brownian condition is that again we pick 2, and we just pick this 2. Okay, so we say we have majority of this one and this one rather than electron holes, because we assume that Kf is much larger than KEL. So this is the reason why. Okay, you'll see that in a minute. Okay, so then the simplified condition is oxygen vacancy concentration is the same as oxygen institutions. If I write that down, so these are protected by Kf, right? Here. So they are square root of Kf. No problem with that, right? All right. Then how do I connect it to the electron and the holes? Basically, again, so that number. Although this chemical reaction doesn't happen a lot, but you have to take that into account. Okay. So again, so we write KO should be oxygen vacancy, then electron square, then PO2 1/2. Okay, now this guy is basically Kf. Okay, then what you get is electron is KO, Kf, then square root, right? Then move the PO2 here, -1,4. Okay. Then holes is basically KEL over electrons. Then you just do the calculation. So what's most important is basically these slopes. Okay. Again, we have here and here. So what about these two guys? Is there any slope? No, right? Because this is a constant in this case, right? It's no PO2 term. Okay, so and we can go back here to draw that. So this is intrinsic, which means that so this is oxygen core. So this is intrinsic. Now what you have is basically these two things that they are the same. Okay. Let me modify this thing a little bit. So this is also in interstitials. Now they are pretty much the same, and this is basically Kf, square root of Kf. Okay. Then what you have is you have holes. Holes again is 1/4 or 1/4 slope, right? So it's positive 1/4, and electron is basically this line here. So this will be holes. This will be electron. Again, so this will be -1/4. Okay. All right. So of course you can guess that the third one will be something like oxygen rich. Okay, so so let's not write all this equation. Let's just look at this part, right? So we already solved for this one, and so this is metric, right? So if I draw a line here, So this is symmetric, right? So this part is just, just copy paste this one in here. Okay. So what I don't want to write anymore. I just let me make it shallower. So this often interstitials, then the holes will be balanced by this one. Again, so the last one will be, this guy cancels out, and basically this guy cancels. Basically the often interstitials and holes, they are pretty much the defect of highest condensation. And again, so we have so now this is the electron. Let's see, now this is often vacancy. Let me just draw it better. Okay. Of course, you can go to the slides I provided to see how we wrote all this equation, and you can do it yourself. Okay. So if we look at this plot, okay, so so there are several remarks I want to make. Okay, so first thing is that the Broadway diagram basically gives you the log defect concentration with log CO2. Okay, so it's double log. Right, so the logarithm here and logarithm here. You can imagine that this is 10 to minus 2, 10 to 2 atmosphere, something like this. Okay. And this fraction will be just maybe just 1 here, 10 to minus 1, 10 to minus 2, something like this. Okay. If I put in numbers. Okay, so it's equivalent to log mu O or mu O2. Or it can be mu. Okay. All right. So it really tells you where to look at, right? So basically tells you the slope of each defect as function of the log Q2. So it can serve as a fingerprint for a lot of defect chemical reaction. Okay. The second one is so we need to know how to convert from Broadway diagram to non-stoichiometry. What does that mean? So basically, if I say it's MO 1 plus delta, let's say the delta is positive, then the delta should be the number of oxygen excess, right? So basically number of oxygen interstitials minus number of oxygen vacancies. Okay. So which means that in this case, from this here now on, we have MO1 plus delta. Okay. So if I say 1 minus delta, the delta, again, so what I want to know is delta is always be positive, right? So then the oxygen integration, basically from this guy now on, it should be MO 1 minus delta. Okay, so there's one very special point, which is this point, or this line here. Okay, this line is that the delta is strictly 0. Which means that not only oxygen vacancy is the same as oxygen interstitial, but also the electron number is the same thing as whole number. Okay. So when I say that it's 1 plus delta is 1 minus delta, it's not exactly the stoichiometry, because although when I say these two are pretty much the same, here in this Broadway diagram, you should know that. So this kind of potential misunderstanding for Broadway diagram. For example, if I draw a line here, okay. So if I draw a line, so from the boundary condition, we'll write oxygen vacancy number should be the same as oxygen interstitial number, right? So here, for example, you say oxygen vacancy should be the same as oxygen interstitial. This is boundary condition we use. However, you also see that the number of electrons here, number of holes here, then it doesn't really satisfy the electron neutrality. So what's really happening here is this is only roughly the same. Okay. So what happens is that this is slightly larger than this one. But how slight? Because remember it's log scale, right? So for example, if 10 to the minus 1 here, the difference can be 10 to the minus 2, because 1 automatically lower. Okay, so when you use boundary condition, of course this is a quite convenient way of solving this. But at the end of the day, you really think of, you really have to think it twice. So therefore, from this point on, you really have delta is large than 0. Just here it's very small. Here it becomes much larger. Okay. So this point here is called a stoichiometric. Stoichiometric point. You should be able to solve for the PO2 for that. Okay. And the third one is to know the thermodynamic parameter. In the plot. Okay. For example, we'll say that the Kf is much larger than KL. How do I know in this plot? So I know that because if I look at here, so this level is basically square root Kf, right? So this level will have the same number of electrons and holes. It's basically square root of KL. You can see already in this plot, the Kf is larger than KL. Right, so it's important to recognize this